Welcome to lesson 7, our smart contract lottery, raffle, sweepstakes, whatever you want to call it, where we go through deploying a truly random, a truly fair decentralized lottery, which is absolutely fantastic. In this lesson, we're going to take everything we just learned and really put it to use, right? There are a couple of things we're going to learn along the way, like events, logging, some other fancy Python things, but for the most part, you have most of the tools that you need to be successful here. So with that, let's jump in. Remember to use the GitHub for help, but let's do it.
Okay, so let's get into our most advanced smart contract project that we've made so far. This is going to be the best example of a full-scale application. And by full scale, I really mean end-to-end, full suite. All of our Brownie, all of our smart contracts are really solid here. What we're going to want to do is create a lottery application where anybody can enter the lottery and a random winner is selected. So let's get to it. And let's get started. So first, of course, we're going to make a new directory. We'll call it smart contract lottery. CD into smart contract lottery, and then open that folder. And great, we are now in our lottery application. So let's go ahead and start a new project. Brownie init, we've got our project here. Now let's create a quick readme.md to explain what we're going to be trying to do here. So number one, we're going to say users can enter the lottery with ETH based on a USD fee. So for example, let's set the price to be like $50 and the users actually pay with Ethereum. So we're going to have to get that conversion rate. Number two, an admin will choose when the lottery is over. And then three, the lottery will select a random winner. Now, something important to note here is since we have an admin here, this means that our application isn't necessarily going to be truly decentralized because we have a single person chooses when the lottery is over. We could scale this out to have maybe a DAO being the admin or something like that, or we could have the lottery automatically open and close based off of some time parameters. But for the moment, this is the setup that we're going to have. Keep in mind, even though this is much less decentralized, it's still going to be a great use of smart contract technology. So first thing that we're going to get started with, of course, is our lottery contract. So we'll create a new file called lottery.sol. And let's begin with our initial setup here. So let's choose our version, pragma, solidity, caret 0.6.6. And this will be the version that we want to work with here. We'll do contract lottery, bracket here. Now let's think for a second on what some of the functions that are going to be, what our main functions are going to be here. We'll probably have a function enter. That'll be public. We'll probably have a function get entrance fee to get the entrance fee of the lottery. We'll probably have a function start lottery that only the admin can call. This will be public as well, which means we'll also probably have an end lottery function. And those are really going to be the main functions. The user can enter based off the entrance fee. We can start the lottery, and then of course we can end the lottery. So let's get started with this enter function just because this is most likely going to be the entry point. As we know, since we're going to want them to pay using this entry function in Ethereum, we're going to need to make this function payable. And in here, we're going to need to keep track of all of the different players, everybody who signs up for this lottery. To keep track of all the players, we're going to make an address payable array. We'll make it public, called players. And anytime somebody enters, we'll just do players.push message.sender. However, right now, we're not checking to see how much value that they're actually sending. We want to set the price of this to be at least $50. So we'll say $50 minimum. So here we're going to have to do a require statement requiring them to do at least $50. In order to do that, we're probably going to need to have some function to get the entrance fee to check whether or not how much they're sending is actually $50. So let's go ahead and make that get entrance fee function now. Since we're just going to be returning a number for get entrance fee, we can probably go ahead and make this a public view and have this return a UN256. To get this entrance fee, we're first going to have stored somewhere what the entrance fee is, we're going to have to store this $50 minimum somewhere. This is something we'd probably want to set right when our contract is deployed. So where can we put stuff like that? Well, in our constructor, we'll do constructor public. We'll create a new variable outside of here. We'll call it uint256 public USD entry fee. And in our constructor, we'll set USD entry fee equals 50. Now, because I like to have units of measure always in way, we'll also do times 10 raised to the 18th. Now we have some USD entry fee. Let's go ahead and get this entrance fee. As we know, since we're going to try to get a conversion rate here, we're going to want to use a Chainlink price feed. So we can head on over to docs.chain.link. We'll scroll down to get the latest price. And we can even just go ahead and copy paste this again. But for the sake of robustness, let's just walk through again how to actually set this up. We're going to need to pull from the price feed to convert $50 to $50 in ETH. So let's go ahead and create an aggregator v3 interface. Internal ETH/USD price feed. And in our constructor, we'll go ahead and set this. We'll say ETH/USD price feed equals aggregator v3 interface. And we're going to want to grab an address from our contract addresses. But of course, as you know, as we've learned from last time, we're going to want to parameterize this. So we're going to want to pass the address of our price feed as a constructor parameter. So we'll do address, price, feed, address, and we'll have our aggregator v3 interface be passed that price feed address. Then of course, since we're using an aggregator v3 interface, we're going to have to import this from Chainlink. So we can just go ahead, copy this from the documentation and paste it right at the top. Or if you want to rewrite it out yourself, feel free to do so. And of course, since we're doing this import here, new file, brownie config.yaml, we're going to want to add this as a dependency. So we'll do dependencies, smart contract kit / Chainlink brownie contracts, and we'll do add 1.1.1 again, and then compiler, soak, remappings, we'll say at Chainlink equals this right here. We'll pull up our terminal and we'll try this out. Do brownie, compile, see if we're doing everything right. We forgot an SPDX license identifier, which is just a warning, but let's add it in anyways. SPDX license identifier, MIT. I should probably spell remappings right. We'll do remappings. And let's try to compile again. All right, lovely. So we at least know that we are compiling correctly here. Awesome. So now that we have a price feed, let's go ahead and set up this entrance fee. So we're of course going to need to get a price from this price feed. So we can even check the documentation on how to do that. We can call this latest round data function. So we could copy paste it. I'm just going to go ahead and rewrite it. But again, we don't need round ID, started at, timestamp, or answered in round. We only need price. So we can go ahead and ignore these variables on our call. So what we'll do is we'll do blank comma, int price, and then comma, 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 equals ETH/USD price feed dot latest round data. And this means we're just going to get the price here. Now we're going to want to do a little bit of quick math. Typically, if we're setting the price at $50 and we have a price feed of $2,000 per ETH, we would just want to do 50 divided by 2,000. But of course, since Solidity doesn't work with decimals, we can't actually just do this. So we'll have to do 50 times some big number divided by the 2,000. So we're going to go ahead and do it like that. But first, let's go ahead and convert this price from int256 to uint256. So we'll say UINT256 adjusted price equals UINT256. UINT256 price. And then, since we know we're going to be using an Ethereum USD price feed that has 8 decimals, let's also just convert it to having 18 decimals as well. So we can also do times 10 raised to the 10th. So now we can have 18 decimals. Now that we have this adjusted price, we'll do UINT256 cost to enter is going to equal USD entry fee times, again, we're going to want to times it by some big number here. So we'll just times it by 10 raised to the 18th. This way, USD entry fee has 18 decimals, but it has an additional 18 decimals here that'll get canceled out with our price feeds, and the math will work, divided by price. And then we'll return cost to enter. Now, of course, since we're doing some interesting math here, it's recommended to use safe math and use safe math functions. We're going to skip over the safe math functions here, again, because in the newer versions of Solidity, you don't really have to use them. But I think it's important to note here that sending this code, this exact code to production would be a bad idea for at least the reason of the safe math functions. But in any case, we have a function here. We think our math is pretty good, but I know for a fact that my math is usually not very good. So let's go ahead and do some testing as we code, just to make sure our get entrance fee function is working properly. So based off of our last lesson, let's talk about how do we want to test this? Well, we could do a mainnet fork here because we're only working with some on-chain contracts and some math. We will at some point have to do our development with Mox and of course our testnet. I kind of want to just do a quick and dirty way. So let's try our mainnet fork just for now, just to see if this is really making any sense. If the current price of Ethereum is $2,500 or this much here, and we want the price of this to be $50, we can do 50 divided by this, and we get 0.019. So this should be approximately what we get for our ETH value. So if we were to write a test lottery.py, we were to test this function, we would expect to get 0.019, or in way, it'll be 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6. We'd expect to get approximately this. So let's go ahead and create a function that tests this. So we'll do test get entrance fee. And in here, we'll deploy lottery. And in here, the first thing we need to do is deploy this lottery function, of course. So we'll do from brownie import lottery. In order to deploy this, we're going to need to get an account. We are going to import our helpful scripts from the last project to this one too, so we can get our get accounts, but for the time being, we can actually just use accounts 0 from brownie. So we'll say accounts 0. Let's just start with def. Then we'll do lottery equals lottery.deploy from account. And of course, we have a parameter here of our price feed address. So we're going to have to add some type of parameter here. For now, let's just hard code it from our config. And we'll go into our config and we'll start our networks flag. We're going to be working, like I said, on the mainnet fork for this quick and dirty here. And we'll call ETH_USD price feed. We'll grab the ETH_USD price feed from mainnet, since we're going to be doing a mainnet fork here. Pop that in here. Now we can just say from config networks network.show active ETH_USD price feed. course, we're going to need to import network here. And now we can do our kind of quick and dirty test. We can do lottery dot get entrance fee. Am I spelling that right? Get entrance fee. Yes. Assert lottery.getEntranceFee should be greater than, let's just go down one, 18. Or if we wanted to make sure we're actually doing this right, we'll do from Web3, import Web3. We'll do Web3.2way 0.019, comma, ether. Should be greater than, and then we'll even do 0.018 just to make sure. And it should be less than 0.022. Now these numbers are of course going to be a little bit different for you. And if you want, you can go ahead and skip this part so that you don't have to do the math. But it is kind of nice to do a quick sanity check saying, okay, like based off what things are right now, what would this price end up to be? Now in our last section, we made a mainnet fork dev network. I'm going to just go ahead and customize our mainnet fork the way that we showed you guys how to do mainnet fork dev. This way you can use accounts and we can be a little bit more robust here. To do this, we're first going to have to delete Brownie's internal built-in mainnet fork. So we'll do Brownie, networks, delete, mainnet fork. Mainnet fork has been deleted. And now let's go ahead and add our own mainnet fork using Alchemy as our Ethereum connection. So you'll want to create a new app. I've already created one here called Smart Contract Lottery. We'll view the key, and this is the HTTP endpoint that we'll use. So to do this, we'll do Brownie, networks, add. This will be a development chain. We'll call this mainnet fork. It'll be a ganache CLI. The host is going to be our local host, so 127.0.0.1. And the fork is going to be equal to our Alchemy HTTP here. We'll do accounts equal 10. That way we can use the accounts. We'll do the new mnemonic equals Brownie. And port is going to be 8545. And great, mainnet fork has been added. Now that we have this here, we can go ahead and run our test. Brownie test -- network mainnet fork. Whoops, it looks like we got a little compile error on our math here. Whoops, it looks like we're divided by price when we need to be divided by adjusted price. And we forgot the parentheses on latest round data. Let's try this again. And I put an extra comment in here. Let's try this one more time. Lovely, and it looks like we're forking correctly. And awesome, it looks like our test indeed passes here. Of course, we know that we're going to want to change this because this isn't a great way to actually test our contracts here, but it can be a nice sanity check. And we know we're going to have to refactor this as well for mocks and for accounts, but we'll get to that in a little bit. Awesome, sanity check complete. Let's get back to our contract here. So we are getting the cost to enter correctly. Perfect. We're getting this entrance fee. What that means we can do in our enter function, we can do require message.value. It's got to be greater than or equal to our get entrance fee function. And if it's not, we'll give them an error of not enough ETH. We have a way for them to enter, and we have a way to get the entrance fee. But we want to make sure that we're not ending the lottery before the lottery even starts, right? Or we're not entering a lottery when a lottery hasn't even begun. So we're going to want a way to iterate through the different phases of this lottery. And we can do that with what's called an enum or an enum. According to the Solidity documentation, enums are another way to create user-defined types in Solidity. We saw an earlier version of doing this with a struct. Enums are a little bit different in that they're explicitly convertible to and from all integer types. So what does that actually mean? Well, we can have an enum like this, action choices, go left, go right, go straight, and sit still. They're just more readable ways to say go left is going to be represented as state 0, go right is going to be state 1, go straight, state 2, sit still, state 3. So for our lottery contract, we're going to want to create this new type that represents the lottery state. So to do this, we'll do enum lottery state open, closed, and calculating winner. This means that we have a new type called lottery state with 3 positions: open, closed, and calculating winner. These different states are actually represented by numbers. So open is actually a 0, closed is actually a 1, and calculating winner is actually a 2. Now that we have this new type, we can create a variable of type lottery state. So we'll say lottery state, public lottery state. And right when we initialize our contract here, we're going to want to set our lottery state to being closed. So in our constructor, we'll do lottery state equals lottery state dot closed. Now, since these are represented by numbers as well, we could also just do lottery state equals 1, because 1 stands for closed. However, it's much more readable to do lottery state dot closed. Now that we have a lottery state, in our enter function, we can require that the lottery state is going to be equal to lottery state dot open. So we can only enter if somebody's started this lottery. And that's exactly what we're going to do in our start lottery function. We're going to do a require in here that the lottery state is going to be equal to lottery state dot closed. And we can even add a failure function in here saying can't start a new lottery yet. And when we do start this lottery, we'll say lottery state equals lottery state dot open. Now, when somebody starts the lottery, they'll be able to enter. Of course, this start lottery bit here needs to be called only by our admin. So this is where our only owner modifier is once again going to come into place. We could write our own only owner modifier, or we can once again use OpenZeppelin's access control and OpenZeppelin's ownable function instead, which is what I'm going to use here. So we're going to go ahead and grab this, copy this, paste it in, import at OpenZeppelin/contracts/access/ownable. And of course, since we're doing this, we're going to have to add this dependency into our config. We're going to be using OpenZeppelin/OpenZeppelin contracts at 3.4.0. We're going to remap at OpenZeppelin equals this. Oops. And then we'll say our lottery is ownable. Perfect. Now we'll try to compile this. Awesome. Looks like Brownie grabbed everything correctly and we're good to go. Great. Now we can finally move into our end lottery function. This is where we're actually going to choose a random winner here. We only want the admin to be the one to actually end the lottery, so let's add the only owner modifier here. And let's talk a little bit about randomness, because this is what we're looking to do now. We're looking to get a random winner here. Now, as you know, the blockchain is a deterministic system, right? And this is super advantageous because it allows us to do all these smart contracts and have this system that can actually reach consensus very easily. Random numbers are much harder. If, let's say, you had a blockchain with a whole bunch of different nodes and each node responds and gives their own random value, well, each node is never going to be able to sync up and say, hey, we all agree on a random number. What you could do is you could base the random number on some other attributes in the system, but then it's not really random. It's actually going to be pseudo-random. So getting truly random numbers in a deterministic system is actually impossible. And if you know a lot about computer science, you actually know that even when you call like math.random in your JavaScript, what your computer is really doing is it's looking at some place in memory, grabbing some value and saying, hey, this is probably random enough. Here, go ahead and use this. Now in smart contracts, especially when working with any type of financial application such as a lottery, having an exploitable randomness function means that your lottery is at risk of being hacked or destroyed. And this isn't even a fairy tale. At the time of recording, about 2 weeks ago, I did a rundown on an exploit where a protocol used insecure randomness and got hacked for $700,000. So I am going to show you this insecure way first. And the reason that I'm going to show you is that it is a quick and dirty way to get a pseudo random number, but please do not use this in any production use cases. I'm going to show you a method that's often used to teach people how to get random numbers, and then we're going to explain why it's so vulnerable and not a good method of randomness. And what some insecure protocols will do is they'll use a globally available variable and hash it. So in your smart contracts, there's actually a number of globally available variables. One of those, as we saw above, is going to be message.value, right? It's going to be the value that's sent with a transaction. Another globally available variable is going to be message.sender. You can actually see a whole list of these different globally available variables in the Solidity documentation here. So since there are all these globally available variables, a lot of times someone will see something like block.difficulty, which returns the current block difficulty. Now, one of these globally available variables is going to be block difficulty or block.difficulty. It's the current block difficulty. Remember how I said that the time between different block generation is called the block time? Well, you can always keep that block time as is by changing the block difficulty over time. The harder the problem or the harder the proof of work algorithm, the longer it's going to take or the more nodes you're going to need to solve that problem. There's this constantly recalculating metric called Ethereum difficulty or block difficulty, depending on the chain that you're working on, that constantly changes. So you might think this would be a great use of randomness, right? Because it's a somewhat hard to predict number. So what a lot of people do is they think that, hey, those sound pretty random. Let's use them as a unit of randomness. And what you'll see like something like uint, Kachak 256, which is, again, this hashing algorithm. And they'll do something like abi.encode packed, nonce message.sender, block.difficulty, block.timestamp, mod, players.length. So I know there's a whole lot going into this line, and let's talk about it. So first, as we can see, is that we're casting or we're converting everything in here to being a uint256. The reason that we're doing this, of course, is because we're going to want to pick a random winner based off of an index, right? We're going to want to pick some random winner in our players array or our players list. So we say, okay, whatever number that we're going to use, that's going to be the index of the winner that we're going to randomly pick. Then they use Kachak 256, which is, again, our hashing algorithm. So they hash a whole bunch of variables together. And they do this abi.encode packed. ABI is another keyword for some low-level work. They'll add maybe a nonce in. They'll add the message.sender, block.difficulty, and block.timestamp. Basically, what they're trying to do here is take a bunch of seemingly random numbers, mash them all together in a hashing function, and then say, yeah, this is pretty random. But the issue here is that the hashing function itself isn't random. The hashing function is always going to be exactly the same. Kachak 256 is always going to hash everything exactly the same way. So we're not actually making it more random by hashing it. All these numbers inside are the pieces that actually determine how random it is. So if the block.difficulty is random, then this will be a random method. If the block.difficulty isn't random, then this won't be a random method. And the block.difficulty is not random. Difficulty can actually be manipulated by the miners. And timestamp is predictable. Nonce is predictable, aka transaction number, because in this regard, they're using the nonce as some transaction number. And message.sender is predictable. When using a random number in this way, the hashing algorithm is always going to be the same. uint256 is always going to be the same. We have a predictable number, a predictable address, a predictable timestamp, and then a manipulatable value. So all this is really doing is giving the miners the ability to win the lottery or win whatever lottery that you're working on. So this isn't going to be an effective way to get a random number. This is an unacceptable way to get a random number in our applications. Yes, we do have this only owner modifier here, which means that we are the ones who are going to choose when to call this. So it is still centralized in that regard. But let's just teach you the best practices for working with random numbers right from the get-go so you don't run into any issues. I'll explain what this part is doing in a little bit. In order to get a true random number, we are going to have to look outside the blockchain. The blockchain itself, like I said, is a deterministic system. So we need a number outside the blockchain. But what we can't do is we can't use just an API that gives a random number, right? If that API becomes corrupted, if they're malicious, if they go down, if something happens, etc. What we need is a provable way to get a random number. And Chainlink VRF is actually that solution. Chainlink VRF stands for Chainlink Verifiably Randomness Function. And it's a way to get a provably random number into your smart contract. It has an on-chain contract that checks the response of a Chainlink node to make sure the number is truly random. Using some cryptography magic, it's able to check a number of the parameters that the Chainlink VRF started and ended with to make sure that it's truly random. It's already used for protocols like Avagochi, Ether cards, Pool Together, and a whole bunch of other protocols as well, because it is a secure, reliable, truly provable way to get a random number, which is incredibly powerful in a decentralized system. So that's how we're actually going to get our random number here. So let's work on getting that. What we can do is we can go ahead and head right over to the Chainlink documentation to actually learn how to work with one of these. Let's go over to the Chainlink documentation just to make sure that we get it right. So if we go to the get a random number here, we have all the documentation you could ever want. So if you ever get lost or confused, you can always come right back here to work with it. What we're going to do is we're going to deploy their simple version in Remix version of working with the Chainlink VRF. And we're going to walk through a minimalistic contract to see how it actually works in a contract. So once again, we're hit this Remix button, Remix pops up, and we immediately get this random number consumer.sol in our files that we can check out. So awesome. So here is our files right here. We can see that this is actually using a different chain than what we've been using. We've been mostly working with Rinkeby, but for this demo, it's actually on Kovan. So we can do some work with Kovan here. And remember, if you do want to stay with Rinkeby, you can always go to this contract addresses section of the VRF and grab these addresses to use. So what's going on in this contract? How do we actually use this? Well, as you can see, the first thing that happens is we're importing some code from the Chainlink package. And our contract is inheriting the abilities of this VRF consumer-based contract. So we're going to see what functions we're actually going to use that are inherited from this contract. And the first thing that we notice is we can see that our constructor in here does some weird stuff. It looks like it almost has two constructors. So what's actually going on here? Well, let's look at this VRF consumer-based.sol contract in the Chainlink GitHub. So we can come to the Chainlink GitHub here. We'll go to EVM contracts, or depending on when you're watching this, it's migrating to contracts at some point. We'll go to EVM contracts. We'll go to SRC. So once we're using v0.6, we'll go there. And we'll look at this VRF consumer-based.sol. As we can see, this VRF consumer base that we're importing has its own constructor, and it takes an address for the VRF coordinator. This is the on-chain contract that actually checks to make sure our numbers are random, and the address of the Chainlink token, which we'll talk about ERC20s in a little bit. What we're doing is we're also inheriting the constructor into our contract. So this is our constructor for our random number consumer, but we can also use the constructor of the VRF consumer base. And this is actually how we go ahead and do that. We grab the constructor of the VRF consumer base and plop it in here. Now it's taking two addresses. It's taking the VRF coordinator and the link token. Like I said, the VRF coordinator is a contract that's been deployed on chain that's going to verify that the return of the Chainlink node is truly random. And we're going to use the link token as a payment to the Chainlink node for its services. And then we also have a key hash and a fee defined inside of this constructor as well. The key hash uniquely identifies the Chainlink node that we're going to use, And then the fee is how much link we're actually going to pay to the Chainlink node for delivering us this random number. Now let's talk about a couple things here. In Ethereum, whenever you make a transaction, you have to pay some ETH gas, right? Or transaction gas. This is to pay the smart contract platform a little bit of ETH for performing our transaction. With a smart contract that operates with an oracle, we have to pay some link gas or oracle gas. This is to pay the oracles a fee for their services for providing data or doing some type of external computation for our smart contract. The question that might then follow up is, oh, okay, well, how come I didn't have to pay when we did this price feeds thing? Well, for price feeds, somebody had actually already paid for the data to be returned. And if we go to data.chain.link and we scroll down, we can actually see a list of sponsors here that are paying to get this data delivered. So they're already paying the oracle gas to bring this data on chain for us. Since no other protocol is getting a random number for us, we're actually going to have to pay the oracle gas here. Now, in this contract, we have a function called getRandomNumber, which is going to return a bytes32. And what it's going to do, it's going to call this request_randomness function, which is inherited from this VRF consumer base. If we look in here, we look for request randomness, we can see there's a function right here called request randomness. This function is going to send our oracle fee or the link token, and it's going to call this specific to the link token function called transfer and call. This function is going to call a Chainlink node. Now I'm not going to go into exactly how it's doing that right now, but we will talk about it in a little bit. So we call this request randomness function, and we send the key hash and the fee. Remember, the key hash uniquely identifies the Chainlink node, and the fee is going to be how much oracle gas we're going to pay. If you ever get lost on how much to pay or what the contract addresses are, you can always head over to this VRF contract section and see where the most recently deployed VRFs are, how much the fee is, etc. Now here's where it gets a little bit interesting. Getting a random number actually follows what's called the request and receive style of working with data. Let's go ahead and just try this out, and I'll explain what this means once we see it. Now we're going to save the answer to this random result variable here, and let's just go ahead and try this and see what happens. So we're going to switch to our injected Web3, and since we're now swapping to a new test network, this means that we have to get testnet ETH and testnet link again. We can always look for the link token contracts page to find the most up-to-date faucets. So we'll scroll down, we'll find Coven. Looks like this is the testnet link faucet and the testnet ETH faucet. So here's our Coven faucet. We'll just want to switch from Rinkeby to Coven. We'll grab our address, paste it in, send me a 100 test link. Here's our transaction. We can see we're transferring some ERC20. We'll take this contract address, we'll add it to our MetaMask by copying the address, scrolling down to add token, pasting it in here. I already have the address in here, so I'm just going to go ahead and hit cancel for now. And we'll also want some testnet Coven Ethereum, which looks like this faucet has it. So we'll paste the address in here. I'm not a robot. And we'll do send me 0.1 test ETH. And perfect. Now that we have some testnet Ethereum and some testnet link, we can proceed. We're going to make sure we're on the Coven test network, and we're going to deploy our random number consumer gist here. Let's go ahead and hit deploy. MetaMask pops up. We're going to go ahead and confirm. I didn't explain this fulfill randomness function intentionally. You'll see why in a second. And great, our random number consumer comes up. Let's check what our random result is right now. It's obviously 0 because we haven't got a random number. So I'm going to do something intentionally wrong because there's a good chance that you'll run into this at some point. If I hit get random number right now, we see this error gas estimation failed. We have plenty of ETH. Why would this fail? The reason that it's failing is because the contract doesn't have any oracle gas. So we got that gas estimation failed because we need to fund this contract address with some link to actually get a random number. So we're going to hit this copy button, and this is going to copy the address. And we're going to come into our MetaMask here, and we're going to send this address. We're going to paste it there, swap to link, and we'll send it one link. This is probably overkill because as you saw, The fee is only 0.1, but we're just going to be overkill for now. And great, now that this contract has some testnet link, now we can call this get random number button because we can actually pay the Chainlink node to actually return our random number. So we're going to go ahead and do confirm. And this is fantastic. So we're paying a little bit of transaction gas to make this transaction, to make this request. And then we're paying a little bit of Oracle gas to make this transaction. Now, so the transaction confirmed, but if I hit random result now, it's still going to be 0. So why is that? What's going on? Well, getting a random number like this actually follows what's known as the request and receive cycle of getting data. You can read more about it here in this basic request model in the documentation. So in one transaction, we actually request some data, or in this case, a random number. And then in a second transaction, the Chainlink node itself will make a function call and return the data back to the smart contract. In this case, the function that we're calling is fulfill randomness. It calls this fulfill randomness with byte32 request ID, which is going to be the request number of when we called this, and it's going to return with this random number called randomness. So after we wait a little bit, if we hit random result now, we can see indeed our random number is in here. And again, the reason that it's in here is because we actually had 2 transactions occur. One paid by us when we called get random number, and one paid by the Chainlink node when it called fulfill randomness. Now, I lied to you a little bit. Technically, that VRF Coordinator contract calls this function, and then the Chainlink node calls the VRF Coordinator function, but for simplicity's sake, you can kind of just think of it as the Chainlink node itself is calling this fulfill randomness function. So now that we know how to do this in Remix, let's go ahead and add this to our Brownie project. So actually, before we even do that, we need to require. So before we even get a random number, let's change the state of our lottery. So now we'll do lottery state equals lottery state dot calculating winner. And while this is happening, no other functions can be called, right? This will lock out. Nobody can start a lottery and nobody can enter a lottery while we're calculating the winner. Awesome. So now that we know a little bit more about random numbers and everything that we're doing here, let's go ahead and try implementing this now. So in our Chainlink smart contract docs, of course, we're going to scroll down. We're going to go to our get a random number bit here. We can copy and paste all this code as well into our smart contracts. So the first thing that we're going to need to do, of course, is import the VRF consumer base code. Let's move back over, scroll to the top, and we'll just paste this in at chainlink/contracts/src v0.6 VRF consumer base, and we'll inherit this into our lottery contract. So we'll say the lottery is VRF consumer base, and it's ownable. Let's take a look at this VRF consumer base in the Chainlink GitHub here. If we scroll down to the constructor of our VRF consumer base, we can see it takes these 2 parameters, the address of the VRF coordinator and the address of the Chainlink token. We can use a constructor of a contract inherited in our contract inside our constructor. So what we'll want to do is we'll want to come down to our constructor, and right after this public keyword, we can add any additional constructors from inherited smart contracts. So we'll say constructor, and this is our normal constructor, and then we'll put VRF consumer base. And we'll add the VRF consumer base addresses in here. We know that it's going to be a VRF coordinator address and a link token address. Similar to the price feed, these 2 addresses are going to change based on the blockchain that we're on. So it'll probably make sense for us to parameterize them the same way we parameterize the price feed address. So in our top level constructor parameters, we'll add an address for the VRF coordinator, and we'll pass this to the constructor of our VRF consumer base. Then we'll also grab an address for the link token. So we'll do address link, and we'll pass this to the VRF consumer base constructor as well. Great. What else do we need to make this work? Well, back in the documentation, we can see we need a fee and a key hash. The fee is associated with the link token needed to pay for this request. So we'll make a public variable uint256 public fee. Since this might change blockchain to blockchain, we'll have this as an input parameter as well. So we'll do uint256 underscore fee, and in our constructor, we'll do fee equals underscore fee. We'll set our global variable to fee. And I need a comma here and no semicolon here. What else do we need? Well, we need a key hash. The key hash is a way to uniquely identify the Chainlink VRF node. So we'll create another one. We'll do bytes32 public key hash. We'll add this as a parameter in here. Bytes32 key hash. And then we'll say key hash equals underscore key hash. Perfect. Our contract is coming along great here. Now that we have the main pieces that we need, how do we then request this random number? Well, if we scroll down in the documentation, we can see we have this request randomness function that we need to call. If we scroll back to our VRF consumer-based contract, this request randomness function is a built-in function from the VRF consumer base. So our contract can natively call this request randomness function right in our contract. And you can see it takes a key hash and a fee as its parameters. So right in our end lottery function, we can add this function. And we can see this also returns a bytes32 called request ID. This return syntax is pretty powerful. You can actually identify the name of the variable you want to return right in your function declaration. So by saying bytes32 request ID, we're saying we're going to return a bytes32 variable named request ID. So right in our function here, we can do request randomness, because again, that's this function that we're importing, passing it the key hash and the fee. This will return a bytes32 called request ID. So this is actually doing this and having our function declaration tell us that there's going to be a variable named request ID is going to be exactly the same as if we did bytes32 request ID equals request randomness. Now, this function call follows, again, what we've talked about as the request and receive mentality, the request and receive architecture. This means that in this first transaction, we're going to request the data from the Chainlink Oracle. In a second callback transaction, the Chainlink node is going to return the data to this contract into another function called fulfill randomness. So again, if we look back in our VRF consumer base, we can see it has this function raw fulfill randomness. We can read some of the comments in here saying raw fulfill randomness is called by a VRF coordinator when it receives a valid VRF proof. Raw fulfill randomness will then call fulfill randomness. So there's a little bit of contract tag going on, but it's going to eventually call this fulfill randomness function, which is going to be what we define in here. And that's how our contract is going to know what to do once it gets the random number back. So in our first transaction, we're going to end the lottery, request a random number, and then in a second transaction later on, once the Chainlink node has created a provably random number, it's going to call a second transaction itself based off of what we define. We just have to call it fulfill randomness. And as you can see, it takes a bytes32 request ID and a random number. So in here, we'll do fulfill randomness, takes a bytes32 request ID, and then a uint256 randomness. We don't want anyone else to be able to call this function. We only want our Chainlink node to call this function so we can return a truly random number. So we're going to make this an internal function. It's internal because actually the Chainlink node is calling the VRF coordinator, and then the VRF coordinator is calling our fulfill randomness. So we'll make this internal so that only the VRF coordinator can be the one to call and return this function. And then we're going to give it a keyword of override. This override keyword means that we're overriding the original declaration of the fulfill randomness function. Our VRF consumer base has a function fulfill randomness defined, but it doesn't have any parameters or anything about this function actually laid out. This function is meant to be overridden by us, and that's exactly what we're doing right here. So in this fulfill randomness function, let's go ahead and define what's going to happen once we get this random number back. So before we can process this random number, let's just check to make sure we're even in the right state. So we'll do require. Our lottery state is going to be equal to lottery state dot calculating winner. And if we're not in that state, we'll just say you aren't there yet. My auto format is on for this one, so it's jumping in. Then let's just do another check to make sure we actually get a response. So we'll do require underscore randomness is greater than 0. And if it's not, we'll just say random not found. Now we need to pick a random winner. Well, we need to pick a random winner specifically out of our list of players, our list of payable public players. So our players array is just a list of players. So it's like player 2, player 3, player 4, and they're each at a different index. What we can do then to pick a random winner is to do what's called a modulo function. In fact, let's even open Remix to do an example of this. Remix, let's pop open a new contract. We'll call it mod.sol. We'll do pragma solidity caret 0.6.6. We'll do contract mod. And in here, we'll do a constructor, blank constructor, and we'll get a global variable, uint256, number, and we'll set it equal to 5. And we'll go down to 0.6.6. We'll save, compile, and let's even just get rid of the constructor. Let's now create a function called doMod. We'll take a uint256 mod value, make this a public function. Public view returns uint256, and we'll just return 5 modulo mod value. Now let's go to JavaScript VM. We'll deploy this. We'll go in here. So our number is right now 5, and let's learn about how the modulo works. If we have this doMod function, what we're doing is the module divides by the number and returns the remainder. For example, if we did 5 mod 5, what do you think we're going to get? So we're going to do 5 divided by 5 and then return the remainder. Well, 5 divided by 5 is 1, and there's no remainder. There's no decimal there. So 5 mod 5 should be what? 0, exactly. Well, what's 5 mod 4 then? Well, 4 can go into 5 evenly once, but there's one number left over. So 5 mod 4 is going to be 1. 5 mod 3 is going to be 2. 5 mod 1 is going to be 0, right? Since 1 goes with everything. This is how the mod function works, and it's this little percent here. We can use that mod function in our fulfill randomness with the length of our players. So we can say uint256 index of winner is going to be equal to the random number that we got modded by the players dot length. So let's say, for example, we had 7 players sign up and our random number was 22. Well, we want to get one of these random 7 players. So we would do 22 mod 7. 7 divides evenly into 22 3 times with 1 left over. 7 times 3 equals 21. Difference between 21 and 22 is 1. 7 times 4 is 28. So we know, this is how we know we've reached our upper limit. So this is how we can get a random number based off of the index. Now that we have this index, what we can do is we can say the winner equals players of the index of winner. And just to keep track, let's make a new variable called recent winner at the top. We'll do address public recent winner. We'll grab this recent winner. Instead of winner, we'll say recent winner equals players in this index of winner here. Now that we've got a winner, well, we want to pay them all of the money gathered from our enters here. So what we can do is we'll do this recent winner dot transfer the entire balance of this address. So we'll say address of this dot balance, and perfect. We'll transfer them everything that we have. Then of course, we're going to want to reset the lottery so that we can start from scratch. We can start blank again. So we'll do players equals new address payable array of size 0. So we're just resetting players to just be a brand new array. Then we're going to change our lottery state to being lottery state.closed because the lottery is now complete. And I often also like to keep track of the most recent random number. So at the top, I'll do a uint256 public randomness variable. And in our fulfill randomness, I'll say randomness now equals underscore randomness. And perfect, we now have a contract here. Of course, we haven't actually tried it out, but we're assuming that it works great. So you know what this means. It's time to go into testing mode, testing and development mode. But let's even just try to do a brownie compile first. Looks like we have an issue here. Send and transfer are only available for objects of type address payable, not address. Oops. Looks like we made our recent winner just an address, but it needs to be an address payable. So let's try brownie compile again. And beautiful, we at least know it's compiling, so that's a great sign. Let's now move into our testing and development phase. As you are starting to figure out, we can ignore these file import callback not supported bugs in VS Code for now. I'm sure the Solidity linter will get better as time progresses. But great, so now let's go ahead and move into actually testing and working with everything here. So let's go ahead into our scripts, and we'll make a little deploy script first. Let's do a new file. We'll call it deploy lottery.py, and let's go ahead and deploy our lottery. So same as always, we'll do def main. We'll come up with a new function called deploy lottery, and then we'll do def deploy lottery, and then we'll just have a pass for now. And if we run this, brownie runs scripts, deploy lottery.py. Our default network is not defined, which means the default is going to be development. And we can even be verbose here, development, write that in our brownie config. Run this, a ganache will get spun up, and nothing will happen because our deploy lottery function doesn't do anything right now. Awesome. The first thing we need always to deploy a contract is we need an account. So we'll do account equals, and we've been using this get account function for some time that we've been adding in a helpful script section so that it can pull from a real testnet or from a local development environment if we like. So to do this, of course, let's create our new helpful scripts.py. We'll create our init__init__.py so that Python recognizes it as a package. And in here, we'll create a new function, def get account. For now, we'll just have it pass. We'll copy this into our deploy lottery. We'll do from scripts.helpful scripts import get account. Now this is what our get account looked like in our last project. Along with that, we had these forked local environments. We also had from brownie import accounts and network and config to make this look really nice, right? Let's flesh this out just a little bit more so it's even more robust. Right now, as we know, we have a way to use Brownie's ganache accounts, and we have a way to use our environment variables. However, there was a third method that we learned that isn't identified here. accounts.load. And this is with our ID. If you still have your account and you still have all your brownie set up, if we do brownie accounts list, you'll see we have a couple accounts here. We want our get account to be even more liberal so that if we wanted to use one of these as well, we could. So let's modify our get account script here a little bit. Let's first get rid of this else and rid of this indent. What this will do is this will be our default. If nothing that we define prior to this is defined, we'll just default to grab right from our config. Which, since we are doing that, let's create our .env. We'll paste our different variables in here, our private key, Web3 Infura, and Etherscan token. And in our brownie config, of course, we'll do wallets from key, private key. And now let's flesh this out a little bit. Let's add an index and an ID. Index equals none, and ID equals none. This way, if we pass an index to our getAccount function, we'll just use an index from this accounts variable. If we pass an ID, we'll have trying to do this accounts.load here. So now let's change this up a little bit. We'll say if an index was passed, we'll just return accounts on that index. Otherwise, if we're doing a local blockchain, we'll just return accounts 0. But if there's an ID, we'll return accounts.load ID. Whoops, we need to actually move this up a little bit so that it's before our local blockchain checking. So now in our deploy lottery, we could do something like get account ID equals freeCodeCamp. Whoops, and this is actually freeCodeAccount. freeCodeCamp account. Let's try one more time. And it's going to ask for our password here. Now we have a much more liberal getAccount function. So now that we have account, we can actually deploy our lottery. So we'll say lottery equals lottery.deploy. And this is where we're going to import from Brownie, import our contract lottery. And we're going to have to add in all of these different variables. So if we go back over to our lottery contract, we need to give it a price feed address, a VRF coordinator, a Chainlink token, a fee, and a key hash. Now, the way we did that in FundMe is that we did it in a way where we checked to see if we were on a local chain or not. If we weren't on a local chain, then we would just pull our addresses directly from our config. If we weren't on a local chain, though, we'd deploy some mocks and use the address of those mocks. We're going to want to do the same thing here, but let's make our lives a little bit easier. We can take this whole process and put it into its own function. So let's make this a little bit easier mentally. The first thing that we're going to need is this price feed address. If we're on a real testnet, of course, we would just go into our Brownie config and add the address, which we will do. We'll add our RinkB network here in a little bit. But for now, don't worry about that. But if we're not on a RinkB chain, what we're going to need to do is deploy our mock. We're going to wrap all of this mocking and checking into a single function called getContract. And we're going to add this function in our helpful scripts. So let's create this function called getContract. So we'll do def getContract. Pass. And let's talk a little bit about what we want this function to do. Let's add 3 double quotes here and 3 double quotes here to start what's called a docstring. This will define everything about this contract. So we're just going to say this function will grab the contract addresses from the Brownie config if defined. Otherwise, it will deploy a mock version of that contract and return that mock contract. For the arguments of this chain, we're going to take a contract name. This is going to be a string, and it'll return a contract. Or in particular, it's going to return a brownie.network.contract. .contract.project contract, the most recently deployed version of this contract. So for example, if we have a Mock V3 aggregator contract, it'll do the most recently deployed version of that with this -1 syntax. Now this get contract function, if this is a little confusing to you, again, we're going to go over this Chainlink mix in a little bit. And inside of this, it has a more robust description of what's going on in this get contract bit. So you can check that out if you want to learn more. But let's go ahead and actually define this. So we obviously want a contract name as an input parameter. So let's go ahead and add contract name in here. Meaning that this get contract function will get something like ETH/USD price feed, right? That's going to be the same as what's defined in our Brownie config. And from this name, we're going to get the type of contract that it is. Contract type. And to do that, we're going to have to create some mapping that'll map the contract names to their type. So right above, we're going to do contract to mock. And we're going to create a mapping in here, which will map everything out. So an ETH/USD price feed is going to be of type Mock V3 aggregator. So we're going to have to import Mock V3 aggregator from Brownie. So now we're saying anytime you see ETH/USD price feed, you know that that's going to be a Mock V3 aggregator if we need to deploy a mock. So we'll say contract type is going to equal contract to mock of the contract name. Now we need to check, okay, do we actually even need to deploy a mock? So sure, let's check if we're on a local blockchain. So we'll say if network.showActive is in our local blockchain environments. And we'll skip the forked local environments because, again, we don't need to deploy a mock price feed address on a forked local environment. We'll say if network.showActive is in the local blockchain environments. Then we'll check to see if one of these contracts has already been deployed. We'll say if the length of contract type is less than or equal to 0, then we're going to go ahead and deploy mocks. So this is equivalent to doing something like mock v3 aggregator.length. We're checking how many mock v3 aggregators have actually been deployed. If none have been deployed, we're going to go ahead and deploy them. So we're going to have to create this deploy mocks function. So we'll do def deploy mocks. And this is going to be the same as what we did in our Brownie fund me, right? It's going to be the exact same. So we'll say account equals get account. I'm not going to put the prints in here, but you absolutely can. We'll say mock price feed equals mock v3 aggregator deploy. We'll need to give this some decimals and an initial value. So right above, we'll do decimals equals 8, initial value equals 2000, 1, 2000, 1, 2, 3, 4, 5, 6, 7, 8. And in our deploy mocks, we'll say decimals equals decimals, initial value equals initial value. To deploy decimals and initial value. Of course, this is going to be from account. And for now, that's it. We'll just say print deployed. All right, great. So now we have a way to actually deploy the mock price feed here. So let's go back up to our get contract function. So we have a way to deploy the mock if one already isn't deployed. Now what we're going to want to do is we want to get that contract, right? We're going to want to get that mock. So we'll say contract equals contract type -1, right? So this is going to be equal to doing mock v3 aggregator -1. This is saying, hey, let's grab the most recent deployment of the mock v3 aggregator, which is exactly what we want. Perfect. So this will work perfectly for our development context. However, we're not always going to just want to deploy to a development network. We're also going to want to deploy to testnets. So then we'll say else, and this is where we'll just grab that contract from the Brownie config. For example, ETHUSD price feed. So we'll say contract address equals config networks network.show active, and that contract name. For example, again, if it's ETHUSD price feed, it'll be ETHUSD price feed here. And the way we're setting it up, it's got to be the same as what's in our contract to mock dictionary here. So up here, the way that we did it was we actually got the contract because we had its contract type based off of Brownie. For here, we're going to have to interact with the contract, getting those two pieces that we always need, which are going to be the address. We actually have the ABI from our Mock V3 aggregator type right here, and we just got the address. So we can create this new contract type by saying contract equals contract dot from ABI, and this contract package can be imported right from Brownie, and it has this function from ABI that allows us to get a contract from its ABI and its address. So we'll just give it a name. We can say contract type dot underscore name. We can do the contract address, and then the contract type dot ABI. So these Mock V3 aggregators and all these contracts have a .ABI attribute that returns the ABI. They also have a underscore name, which returns their name. So this is perfect. This is how we'll get the contract otherwise. And then at the end of all this, we'll just do return contract. Awesome. So this is an incredibly powerful function for us to get a contract based off of if it's already deployed as a mock or it's a real true contract. I know there's kind of a lot here, but definitely check the GitHub repository if you're a little bit confused on what's going on with this function. And let's also just deploy this to make our linter happy. Why not? Yay, VS Code's happy now. But now that we have this function, let's go back to our deploy lottery. Now we can do a comma, get account, and now we have a get account function. So let's go through this again. This lottery.deploy get account is going to get an ETHUSD price feed. If we don't have a mock deployed, it's going to deploy a mock price feed for us, and we're going to return that mock price feed. However, if we're on a test net, if we're on a real network, we're going to grab its actual address and return a mock contract of it. Our mock contract here has all the same functions of a regular contract, so we can just use it as the same. This way, we don't have to adjust this function for whether or not we're deploying to a test net or to an actual address. The only additional piece we should put in here, just for clarity, is we should add .address here, because this is going to return the actual contract, and we really only want the address. This is going to make our coding a lot more robust for moving between development environments and testnet environments and working with scripts in a really effective manner. So now that we have this incredibly powerful function, let's go back to the lottery and figure out what are the different pieces we need in here. Okay, great. We also need a VRF coordinator. So to do this, we're going to go back to our docs.chain.link. We'll go to contract addresses, and we could do mainnet here, but let's also just set this up to work with RinkB. So we'll do Control F for RinkB. VRF coordinator is going to be this address right here. So we'll copy it. We'll go back, and we're going to have to do in our config is we're going to have to add a new network here for RinkB. We'll do VRF Coordinator. Will be that address right there. And then while we're doing this, let's also get the RinkB address for our price feed. So Ethereum price feeds, RinkB. Let's scroll down for ETHUSD. ETHUSD, here we go. Grab that, enter, and this will be ETHUSD price feed. Paste that address in here, perfect. So now we can do get contract VRF coordinator .address. Of course, we are going to have to go back to our helpful scripts because there's currently no mapping between what a VRF coordinator is and what its mock needs to be. So we'll add a comma here, and we'll do VRF coordinator, and we need to get a mock VRF coordinator. Well, first of all, we don't even have our Mock V3 aggregator, so let's go grab that as well. So we can grab both of these. Again, I'm going to highly recommend going to the Chainlink mix, going into the contracts here, going to the test folder for these different mocks, because these are already set up to work with the Chainlink mix. However, you can definitely go into the Chainlink GitHub as well. Go to contracts, SRC 0.6, tests, and then look for the different mocks in here. So Mock Oracle, VRF Coordinator mock, etc. So I'm just gonna grab it though from this Chainlink mix. So let's go to VRF Coordinator mock, and I'm just gonna grab this whole thing here. So do contracts, new folder, test, new file, VRF Coordinator mock.sol. Paste it in here. And then while we're in here, we'll want to do a new file, mock v3 aggregator.sol. We'll grab this as well from our Chainlink mix. Again, it's got all the functions of a price feed, update answer, latest round, etc. VRF Coordinator mock has different functions for actually working with the VRF Coordinator. One of the specific ones in particular is this callback with randomness that we're going to use in our tests. So our VRF Coordinator is going to get mapped to our VRF Coordinator mock, which will also import this from Brownie. Great, and just to double check everything's working, we'll want to run just a quick Brownie compile to make sure we are importing our mocks correctly and everything's compiling, so it looks like we're good there. All right, so now we have get contract VRF coordinator.address. Perfect. What else do we need in here? We need a link token. The Chainlink token is, of course, just another smart contract. So we're going to do the exact same thing here. Get contract link token.address. Of course, this means in our config for RinkB, let's add a link token address. We'll go to the Chainlink documentation. We'll go to link token contracts. We'll look for RinkB. We'll grab this address. We'll drop it in here. Perfect. Now we have it in our Brownie config. We'll also need to add it to our helpful scripts. So we'll need a mock link token, which again, we can just go ahead and grab from our Chainlink mix here. So we can go to test. And as you can probably see, what I often normally do is literally just copy this entire test folder project to project. So I'm going to copy this whole thing, create a new file. We're just going to call this one link token.sol. Contract link token, perfect. And then in our helpful scripts, we're going to have this be link token. And of course, we're going to import this from Brownie. Great, get contract link token.address, perfect. What else do we need? We need a fee and a key hash. So the fee and the key hash are both just numbers, right? These aren't actually contracts. So we don't need to put this through that get contract bit. What we can do is just in our config, in our development network, we can just add a default for the key hash and for the fee. I'm just going to set my development key hash and fee equal to the RinkB ones. So to grab those, we'll go to the Chainlink docs once again. We'll scroll down to using randomness, contract addresses. We'll look up RinkB. We'll grab the key hash here, which we'll paste in for both our development and RinkB. And then the fee, it says 0.1 link. So we'll just do that in way here, which will be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7. And we'll do this line for RinkB as well. Now in our deploy lottery, we can just grab this directly from our Brownie config because we're always just going to have this default key hash and this default fee here for our development network. So we'll do config networks network.show active. Which one's first? The fee. Of course, this means we're going to have to grab network from Brownie and also config. Then we'll do config networks network.show active key hash. And then, of course, our last bit here, from account. And then, additionally, as we learned last time, if we want to publish this, we'll do publish source equals config networks network.show active. We'll say .get verify, and then we'll add this false bit here. What this is saying is get that verify key, but if there's no verify key there, just default to false. This way, if we don't set a verify key in development, that's fine. It just won't get verified. For RinkB, let's go ahead and set verify to true. So we can actually verify this on the RinkB chain. And then we'll even do a print statement here. Deployed lottery. All right, lovely. Let's try this out. We'll do Brownie, run scripts, deploy lottery.py. We won't set a network flag, so it'll go to the default development network. Let's try this out. Things are compiling. Ganache is spinning up. It looks like we did run into a little issue here with our get contract function. Of course, we forgot to add deploying these mocks in our deploy mock script. Whoops. Let's go ahead and add that as well. Right now, our deploy mocks only deploys the Mock V3 aggregator. So let's add the rest of our mocks in here. We're going to need to deploy a VRF Coordinator mock and a Chainlink token mock. So let's open up those contracts, see what they need. The link token for a constructor doesn't have a constructor, so we can just have it be blank. So we'll do link token .deploy. And all we need is a from account here. And then let's see what that VRF Coordinator mock takes. VRF Coordinator mock. It takes the link token as an address. Perfect. So then when we deploy the link token here, we'll say link token equals link token.deploy, and then we'll do VRF Coordinator mock .deploy. And then we'll use the link token.address as an input parameter, and then of course from account. All right, so now we're deploying all three of those mocks right away. Let's try this again. Brownie run scripts, deploy lottery.py. Ganache is spinning up. Perfect. So we can see here that our Mock V3 aggregator was deployed, then our Mock link token was deployed, then our Mock VRF coordinator was deployed, and then our lottery was deployed with those mocks defined. And we deployed the lottery. Awesome. Now we could 100% go ahead and then run this script on an actual testnet, right? Because our config is set up well. Let's write some more functionality for actually interacting with this lottery before we actually do that. And then we can actually just run a script which will do all this functionality end to end. Because again, deploying to a testnet takes a long time, and we really only want to do that when we're done and we're fairly confident that everything's working well. Let's even just delete this here. So now what's the next thing that we'd want to do here? What's the next thing we want to do in a script here? Well, we'd probably want to go ahead and start the lottery. So let's write a script that can actually do that. We'll do def start lottery. And in here, we'll get our account equals get account. We'll say the lottery is going to be the most recent deployment of the lottery. And we're going to call this start lottery function here. This is indeed changing state. So we do have to make a transaction. We'll do lottery. That's start lottery. We'll say from account. And then we'll do a little print and just say the lottery is started. And then in our main function down here, we can even call this start lottery function. So if we run this again on our development chain, we'll see if everything works smoothly here. Okay, we did run into an issue, and this is something that you'll see from time to time. Typically the workaround is you want to wait for that last transaction to actually go through. So we'll say starting transaction equals lottery.start lottery. And we'll do starting transaction.wait 1. Brownie sometimes gets a little confused if you don't wait for the last transaction to go through. So let's try it again, and perfect. We do get this working as intended. So that is a really helpful tip if you run into those weird issues. You'll notice that even when we didn't have this, it still completed successfully. It just got a little confused at the end. All right, cool. So what do we want to do next? Well, we probably want to enter the lottery. Let's do def enter lottery. So how do we enter the lottery? We'll say account equals get account. Lottery is going to be lottery -1. We need to pick some value to send when we call the enter function, right? Because we need to send that entrance fee with it. So we'll say value equals lottery.get entrance fee. And just to be safe, I usually will tack on a little bit of way as well, because sometimes it might be off by like 1 or 2 or something like that. So we'll do lottery.get entrance fee plus, maybe something like this, which is like barely anything. Then we'll do transaction equals lottery.enter. We'll do from account. We'll send a value, which will be value. We'll do tx.wait, and then we'll do print. You entered the lottery. And we'll do this enter lottery bit down here too. Enter lottery. We'll run this, see if our enter script is working appropriately. You entered the lottery, looks great. And let's do our last function here. We'll do def end lottery. Count equals get account. Lottery equals lottery -1. We'll make a transaction, which will be lottery.end lottery. Now, before we actually end this lottery, we're going to need some link token in this contract. Because remember, our end lottery function calls this request randomness function. And we can only request some randomness if our contract has some Chainlink token associated with it. So we're going to need to first fund the contract and then end the lottery. Since funding our contracts with the link token is going to be a pretty common function that we use, let's go ahead and turn this also into a helpful script. So let's go to our helpful scripts. We'll make a new function called fund with link. And let's have this take a couple of parameters. So first, we'll want to have a contract address, of course. We'll want to know who we're going to fund with link. We'll set a default account to being none. So if you want, you can send an account, but you don't have to if you don't want to. We'll also do the same thing with a link token. We'll say if you want to use a specific link token, you can. Otherwise, we'll just grab it ourselves. And then we'll also do a default amount, which we'll set to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, which is going to be 0.1 link. So first, let's get an account. We'll say account equals, and we're going to do a little clever Python stuff here. We'll say account equals the account if somebody sent it, if account. So we're saying the account that we use is going to be this account thing if this account thing even exists. Otherwise, we'll call our get account. Otherwise, we'll just do our regular get account function. Then we'll do the same thing with the link token. We'll say the link token is going to be equal to the link token that somebody supplies as a parameter if they applied something as a parameter. Otherwise, we'll just do that get contract stuff that we did before of the link token. Now that we have this link token contract from our get contract function, which again is basically the equivalent of doing, this contract.fromABI on our link token, pulling from our config or from our mock, now we can just call the functions on this link token. So we can say our transaction equals link token dot transfer. We're going to transfer token to the contract address with a certain amount. And of course, we'll do from account. We'll do tx.wait. And then we'll do print funded contract. And then we'll even return that transaction. I do, however, want to show you another way to work with this using the interfaces. Instead of doing this link token.transfer directly on the contract, we can use this interfaces section to actually interact with some contracts. So right now we have our mock link token in here, which is great because it has all the definitions and all the functionalities defined in here. Sometimes you're going to have contracts that you don't have everything. You don't have all the functionality, and maybe you only have the interface, maybe you only have some of the function definitions. So we can still interact with contracts with just an interface because, again, that interface will compile down to our ABI. So as another way of teaching us how to actually work with some of these contracts, what we can do is we can use the link token interface basically the same way as we used the link token contract here. So again, I'm in my Chainlink mix because there's already a link token interface in here. And this will compile down to a way that our Brownie package knows how to interact with these contracts. So if you wanted to, we could just grab this, go to our Brownie section. We'll do a new file in interfaces. We'll call it link token interface.sol. We'll paste it in here. Save my auto formatted here. And what we can do in our helpful scripts instead is transaction equals interface. And we can also just import interfaces right from Brownie. Interface dot link token interface. And we just need to give it a contract address. So we can say link token.address. We can say the link token contract equals interface.linkTokenInterface, linkToken.address. So this is another way we can actually create contracts to actually interact with them. So we saw up here this contract.fromABI, which is great. This is another way we can do that exact same thing. So then we can just do linkTokenContract.transfer, contract address, amount from account. We'll say this is TX equals. So this is another way to actually interact with contracts that already exist. You're probably starting to see that Brownie has a lot of built-in tools that make it really easy for us to interact with contracts. If we have the ABI, we can just pop it into contract.fromABI. And again, with the address and the ABI, and then just give it some name. If we have the interface, we don't even need to compile down to the ABI ourselves because Brownie is smart enough to know that it can compile down to the ABI itself. And we can just work directly with that interface, which is incredibly powerful. For now, I'm going to comment these two lines though, and we'll just use the link token.transfer for now. Now that we have a funding script or a funding function, we can import this from our helpful scripts. From scripts.helpfulscripts, import get account, get contract, fund with link. And we can just call in our end lottery function, we'll do fund with link. And parameters, we only really need a contract address because the way we set this up, we'll just automatically grab a default otherwise. So we can say lottery.address, and that's it. And that's all we need. And then I know we're doing tx.wait right in the fund with link, but just to be verbose here, we'll get the transaction from the fund with link, and we'll do tx.wait here as well. And then once we're funded with link, then we can go ahead and call our end lottery function, because again, this is going to call that request randomness function from the Chainlink VRF. We'll do ending transaction equals lottery.end lottery. And all we have to do is from count do ending transaction.wait 1. So from our end, this is really all that we need to do, right? But remember, when we call this end lottery function, we're going to make a request to a Chainlink node, and that Chainlink node is going to respond by calling this fulfill randomness function. So we actually have to wait for that Chainlink node to finish. Now, typically, it's within a few blocks. So normally what we can do is we can just do a time.sleep for something like 60 seconds, and typically in that time, the Chainlink node will have responded. So we'll just do import time at the top, time.sleep, and then we can see who that recent winner is, if that Chainlink node responded with a recent winner. So we can say print f lottery.recent winner is the new winner. All right, now, of course, for those of you who are thinking ahead a little bit, you might be thinking, hey, well, there's no Chainlink nodes watching our local ganache. And you're exactly correct. So what happens when we add our end lottery function to our main function here? Do you think that we're going to actually get a recent winner back? Why or why not? What do you actually think? Well, let's give it a shot. We'll do brownie, run scripts, deploy lottery.py. So we're doing a lot of transactions here. We've started the lottery. We're entering the lottery. You entered the lottery. We're sending some link token. Now we just called the end lottery function. While we're waiting here, this is when the Chainlink node would go ahead and start responding with our randomness. However, as you probably astutely guessed, there's no Chainlink node that's going to call this fulfill randomness function right now. So for our Grenache chain, this will hypothetically end with nothing, right? Because there's no Chainlink node actually responding here. 0 is the new winner. Of course, this means that the Chainlink node actually didn't respond because there is no Chainlink node on our local Grenache. For our testing purposes, we're going to figure out how to actually get around that and deal with that. Awesome. It looks like we have everything set up to be successful in our lottery here. But we want to do our due diligence. We want to make sure that our tests are really solid on a development chain before we actually test this on an actual testnet. So let's jump into some of these tests. We've already started with this test lottery.py bit here, but we're going to iterate on this and make this even better. Now, before we get into these tests, there's a couple of things we want to talk about here. And that's going to be integration tests and unit tests. Unit test is a way of testing the smallest pieces of code in an isolated system. And we're going to use it to loosely define testing independent functions in our lottery contract. We also want to do what's called integration testing, which is going to be testing across multiple complex pieces. Typically, I like to run my unit tests exclusively on a development environment and my integration tests on a testnet. This is really helpful because we can test the majority of our application, like we said, on a development network, and then still be able to see what actually happens on a real testnet and see what happens on Etherscan and everything like that. Typically, what people do is inside their test folder, they'll create two different folders, one for unit and another folder for integration. Since for this demo, we're only going to have one file for both, I'm just going to go ahead and not create these folders, but it's a pretty common practice. Instead, what I'm going to do is I'm going to rename this. I'm going to hit enter to rename it. I'm going to do underscore, type unit for unit tests, and we're going to create a new file called test lottery integration.py. So this one will do our integration tests, and in this one, we'll do our unit tests. Now, when writing unit tests, we really want to test, hypothetically, every single line of code in our smart contract. This is incredibly important, of course, because smart contracts are open to everybody to see and interact with. So we really want to test every single line of code we have in here. So let's go ahead and finish writing a get entrance fee test that will work on a local development network. As you can see, we're already going to have to refactor this from what we originally had. Let's go ahead and just delete everything under here for now. We already learned so much more from there. All right, so how are we going to test this get entrance fee function now? So first, we're going to want to deploy our lottery again. since we have a deploy lottery script already, we can just use this deploy lottery script as well. If we wanted to, we could just copy paste this whole part into our test, but we're just going to go ahead and work from this deploy lottery script. So we're going to import this, and then we can actually even get rid of this from Web3 line for now. We can get rid of these two comments too. And we'll say from scripts.deploy lottery import deploy lottery. And on this deploy lottery function, we'll just say lottery equals deploy lottery, and we will return our lottery. Now in our unit test, we'll say lottery equals deploy lottery. And this will give us our lottery contract. Once we have our lottery contract, we can just call this get entrance fee. So we can say entrance fee equals lottery.get entrance fee. And oops, let's just make sure we're doing the arrange act assert mentality here. And we're going to want to make sure this entrance fee is what we expect it to be. So what do we expect it to be? Well, again, our helpful scripts is going to deploy these mocks, right? It's going to deploy this mock, and the initial value is this 2000 number. So if the price of ETH here is $2,000 ETH USD feed, and the USD entry fee is 50, we'd say 2000 over 1 is equal to 50 over X, which is going to be equal to 0.025. So we can go ahead and even do this math here. We can say expected entrance fee is going to be equal to 50 divided by 2000. We'll just do 0.025, but we'll do this in way. So we'll do from Web3 import Web3. We'll say this is Web3.2 way 0.25 Ether. And now we'll assert our expected entrance fee equals the entrance fee. And now to test this, we'll do brownie test-k. And perfect, this is working exactly as we anticipated. So that's awesome. Now, as we mentioned, since this is a unit test, we really only want to run this when we're working on a local environment, a local blockchain environment, or a local development network. So we'll go ahead and do this with PyTest again. Say if network.showActive is not in local blockchain environments, pytest.skip. Of course, we're going to have to import PyTest. We're going to have to import this local blockchain environments from our scripts.helpful scripts. My VS Code automatically added that bit here. Now, if we try to run this, brownie test -k get entrance fee -network rinc eb, it should go ahead and skip this. Perfect, and that's what it does. What's the next piece that makes sense here? Enter is going to be one of the first things that these developers do. So let's do test def test enter. But let's even be more specific than that. We don't want people to be able to enter our lotteries unless the lottery is actually started. So let's make sure that this line actually works. So we'll call def test can't enter unless started. And again, we're only going to run this on a local development chain. So we'll just copy paste this section down here. We'll say lottery equals deploy lottery, because we're going to want to work with the lottery. And now we're going to want to, that when people try to enter a lottery that hasn't started yet, it's going to revert. So we can use what we've used before. We'll say with pytest.raises exceptions.virtual machine error lottery.enter from get account value lottery.get entrance fee. Of course, we're going to have to import both get account from our helpful scripts and exceptions from Brownie. Perfect. And this as well is following the arrange This is actually act/assert. So let's go ahead and test this. Brownie test-k. Test can't enter unless starter. Oops, let's do start ed. And great, that's passing as well. Let's go ahead and keep going down this list. What else? Now that we've tested whether or not they can't enter, let's test whether or not they can enter. So we'll do def test can start and enter lottery. So we're going to copy this again, paste it down here since we're going to work on a local blockchain. We'll do lottery equals deploy lottery. Account equals get account. We'll start the lottery. Lottery.start lottery. We'll do from account. We'll do lottery.enter from account. Say value is lottery.get entrance fee. And then we'll assert that we've correctly added a player to this lottery. So we'll assert lottery.players of 0 is going to be this account, right? Because we have our players array, and we're going to assert that we're pushing them onto our array correctly. Lottery.players of 0 equals account. So here's our act, and here's our assert. So let's try this now. Brownie test-k, test can start and enter lottery. And once again, awesome. Things are looking great. Now, let's test to see if we can actually end a lottery. So we've tested we can start a lottery. So we'll do def test can end lottery. We're going to copy this again, paste it down here. We'll do lottery equals deploy lottery. Account equals get account. We'll start the lottery with lottery.start lottery. Now we could 100% just import the rest of these functions in here, like end lottery, enter lottery, and start lottery. And similar to how we're just doing lottery equals deploy lottery, we could absolutely do that. For being very verbose here, I'm just going to go ahead and write all the functions and transactions myself. And this way, we'll actually be able to test a little bit more granularly. Anyways, we'll do lottery.start lottery from account. We'll do lottery.enter from account. We'll give it a value. Lottery.get entrance fee. Oops, I'm going to have to do account, of course, equals get account. Now, to actually end the lottery, we do need to send this some link because we're calling request randomness. We use our fund with link script that we have in our helpful scripts. We'll import this from our helpful scripts. We'll call fund with link on our lottery contract. Once we fund with link, we'll then call lottery.endLottery from account. And then how do we actually know that this is being called correctly? Well, if we look back in our lottery contract here, when we call end lottery, we're not really doing a whole lot. All we're doing is changing our state. So let's go ahead and check to see if our calculating winner state is different. So we'll say assert lottery dot lottery state is equal to what? So calculating winner, if we scroll up to our enum, is in position 2. Open is 0, close is 1, calculating winner is 2. So we can say assert lottery.lottery state equals to 2. We can go ahead and test this as well. We'll do brownie test-k, test can end lottery. We'll see if this works. And it does. Now let's test the most interesting piece of this entire lottery contract. We're going to test whether or not our fulfill function actually works correctly. does this correctly choose a winner? Does it correctly pay the winner? And does it correctly reset? So let's go ahead and build our most complicated and most important test of this whole contract, choosing the winner. We'll do def test can pick winner correctly. Let's copy paste this bit about getting started. We'll do lottery equals deploy lottery. Account equals get account. We'll do lottery dot start lottery from account. And then we'll enter with a couple different players. We'll do lottery dot enter. Well, let's say from account value lottery dot get entrance fee. Lottery dot enter. And we'll copy this 2 more times, but instead we use some different IDs. We'll do index equals 1, and we'll do index equals 2. These are going to be different accounts here because we're going to use a different index because we want to just test for multiple different people here. This unit test is getting drastically close to being an integration test, but as I said, we're being a little bit loose with the definitions here. Now we're going to want to fund it with link, so we can just go ahead and copy this line here, fund with link lottery. And now we're going to want to choose a winner here. And this is where we actually have to modify one more thing in our lottery contract. So in order to test actually calling this fulfill randomness function and testing everything in here, we're going to need to call this fulfill randomness function. Now, if we look at our VRF coordinator mock, we have this function called callback with randomness. And this is the function that actually calls this raw fulfill randomness.selector, which eventually will call that fulfill randomness function. But this is the entry point that the node actually calls. We have to pretend to be a Chainlink node and call this function. We're going to return a random number, of course. We're going to choose the contract we want to return to, but we also have to pass the original request ID associated with the original call. Now in our lottery contract, our end lottery function isn't going to return anything. And even if it did, it would be really difficult for us to get that return type in our Python. So what we want to do to keep track of when this contract actually entered the calculating winner state is we want to do what's called emitting an event. Events are pieces of data executed in the blockchain and stored in the blockchain, but are not accessible by any smart contracts. You can kind of think of them as the print lines of a blockchain or the print statements of a blockchain. We can go to this logs section, which also includes all the different events. Now, there's a lot of information here, so we're actually going to do an event ourselves just so that we can see what this really looks like. You can see here that when we call this end lottery function, in the logs, if we scroll to the bottom, there's an event here called randomness request. This was spit out by the VRF coordinator. This was spit out by the VRF consumer base that we inherited. And it even has some data that's already been decoded. One of those pieces of data is the request ID. Now, to add an event, we first need to create our event type. So at the top, we'll go ahead and do event requested randomness. We'll say bytes 32 request ID. So now we've identified a new type of event called requested randomness. It's really similar to the enum in this regard. To emit one of these events, all we have to do in our end lottery bit is we'll do emit requested randomness and then request ID. Because requested randomness takes a bytes 32 as an input parameter, and we're going to pass it that request ID as an input parameter. Now that we have this event being emitted, back in our test, when we call end lottery, it will actually emit one of these events to our transaction. So what we can say then is transaction equals lottery.end lottery. Same way we've always done it. But now we can look inside of this transaction object. Inside of this transaction object is actually an attribute called events, which stores all of our events. We can then look for a certain event name, which we know is requested randomness. So we'll say, out of all the events, look for the requested randomness event. And in there, in that requested randomness event, find the request ID. Request ID. Now we can say request ID is going to get grabbed from this event that we emit. So these events are going to be really helpful for writing tests. These events are also really helpful for a number of other reasons. One of the big ones is upgrading our smart contracts or understanding when a mapping is updated. But for now, we're going to be using them for testing. Now that we have this request ID, what we can do is pretend to be the Chainlink node and use this callback with randomness function to dummy getting a random number back from the Chainlink node. So what we're going to do is we're going to call our getContract function and get that VRF coordinator. Of course, we're going to have to import it from our helpful scripts. And we're going to call that callback with randomness function. So we're going to do dot callback with randomness. And we need to pass it this request ID, a random number, and then the contract to return to. So we'll do request ID. We'll do some random number, like we'll say static RNG equals 777. So we'll say the random number that we're going to return is going to be 777. And then we'll do lottery.address because we're going to return it to the lottery. Once again, we're going to say from account because this is making a state change. And now that we've got a callback, what we can do is do our asserts now. So this is us dummying getting a response from a Chainlink node. And this is how we mock responses in our tests to make our lives way, way easier. So now we can figure out who the winner of this lottery actually is. If these are our three entries, that means it's 777 mod 3, since our random number is going to be 777. If we pull out a calculator, 777 divided by 3, it divides evenly, so we know that this means the answer to this is going to be 0, aka our account is going to be the winner. So let's assert the lottery dot recent winner is going to be equal to our account, right? Because we set a recent winner in here. We transfer them some money. We'll assert lottery.balance is now 0 because we're transferring this account all of the money. And let's even make sure that the account gets more money, right? So we'll do starting balance of our account. Starting balance of account equals account.balance, and we'll do balance of lottery equals lottery.balance. And then we'll assert account.balance is now going to be these two added together. Starting balance of account plus the balance of the lottery. Because we should get all of the lottery winnings here. Okay, so this is a long test, but this is probably the most important test. Let's make sure this is doing what we want it to do. So we'll do brownie test-k. Test can pick winner correctly. Let's see if this works. Oops, I forgot to put some parentheses here. Parentheses here. Let's try this again. And perfect. We are actually updating, paying out, and running our lottery correctly and fairly with true randomness. This is incredibly exciting. And we've emitted events in our lottery contract to use in the off-chain event logging of Ethereum. I know we're getting antsy to actually run this on a real chain. So let's go ahead and do our last bit here. We'll create our integration test, which we will run on an actual chain. And then if we wanted to, we go ahead and try our deploy lottery function on a real chain as well. All right, so let's do our integration test here. This is where we're going to actually test on a real live chain. We're going to use Ringby because that's the network that we've been using this whole time, which is great. Now, I'm being a little bit liberal in the way that we're doing our tests here. And we're just going to do one test for this integration test, but keep in mind, you're going to want to test every piece of your code. So let's just create a test called def test can pick winner. Now, this is going to be the opposite of our unit tests. Our unit tests are only going to be on our local blockchains, right? We're going to skip if it's not on our local blockchains. We're going to do the opposite of this one. So we can even just copy this, or we can type it out. We'll say if our network.showActive is in those local blockchain environments, then we're going to do pytest.skip. Of course, since we're grabbing these pieces, we're going to do from brownie import network. We're going to import pytest. And we're going to do from scripts dot helpful scripts import local blockchain environments. We're going to deploy our lottery. So lottery equals deploy lottery, which we're just going to grab from scripts dot deploy lottery import deploy lottery. We'll do account equals get account. Of course, we're going to grab that from our helpful scripts as well. So we'll do lottery dot start lottery. This will be from account. We'll do lottery dot enter. We'll say this will be from account. We'll do some value, which is going to be lottery.get entrance fee. And if we run into an issue here, sometimes, again, we can do lottery.get entrance fee plus like 100 or 1,000 or something like that. This is going to be barely anyway, but for now, let's keep it like this. Then let's just copy this line. Run it again. We'll have 2 people enter the lottery. Of course, it's going to be us both times. And great. Now we're going to want to actually end the lottery. So first we're going to want to fund it. So let's import that funding script. So we'll get fund with link, or that function. So we'll call our fund with link function on our lottery contract here. And then we'll go ahead and end the lottery. So we'll say lottery dot end lottery. We have to do this from our main account. This from the admin account. Now, this is where it's going to be a little bit different from our integration tests, or from our unit tests. In our unit tests, we pretended that we were the VRF coordinator, and we called the callback with randomness. We pretended that we were a Chainlink node. Here, we're not a Chainlink node because we're on an actual network, so we're actually just going to wait for that Chainlink node to respond. So for simplicity, we'll just do time.sleep, and we'll wait like a minute for it to respond. Of course, since we're using time, we're going to want to import time right at the top. And then, since account was the only one to actually be in this, we'll do assert lottery recent winner equals account. And we'll also assert lottery.balance equals 0. All right, great. So we have an integration test that we can run, which is going to run through pretty much the vast majority of our functionality here. So we can go ahead and test this with brownie test. We'll be a little bit verbose here. We'll say -k test can pick winner. And then, of course, we'll do -- network Ringby. Now, before we run this, per usual, we got to make sure, do we have any testnet Ringby Ethereum? We do. Great. Do we have any testnet Chainlink? We do. Perfect. Do we have a .env? We do. It's got all of our pieces. Let's check our Brownie config. .env. Awesome. And again, if you don't want to use the .env, you can use that other method that we showed you guys, how to encrypt with a password that you can absolutely use. Oops, and before we run this, let's set this to start lottery, because that's the actual function here. And we'll also need to be lottery.balance with parentheses here. Sorry about that. And now we can run Brownie test -k test can pick winner --network ring-b. We'll also add this -s flag, which will print out whatever Brownie is going to be printing out. It'll make everything a little bit more verbose here. And if you want to, you absolutely should, because this is something that we'll have to do at some point anyways. However, if for this tutorial you want to skip it, go ahead, because we're actually going to run through this whole process of deploying and waiting again anyways. So now we've added all of our tests, what we can do is run our entire test suite. So we'll do Brownie test. And this is going to run through all of our development tests here. You'll see it'll go really quickly. And you see how much faster it is for us to run our test on a local chain as opposed to doing everything on a testnet. So it's going to make your life way easier. And we have everything passed here. So we know that our contract code is doing approximately what we want it to do. So it's time for the moment of truth. Let's deploy this to an actual testnet. So we have our deploy lottery script, which oftentimes I'll have it be just this deploy lottery bit, and then I'll have some other scripts for these other pieces, or maybe I'll do it in the Brownie console. But just to demonstrate everything end to end, we'll have deploy lottery, start lottery, enter lottery, and end lottery all in this one script, so that we can see everything end to end and see what it looks like on Etherscan. So let's go ahead and run this script on a ring-b network, and then we'll go jump onto Etherscan and see everything. So let's do it. Brownie, run scripts, deploy lottery, network ring-b. So first, we went ahead and we deployed our lottery. We got our addresses with our get contract method. We got our fee, we got our key hash, we got our published source and everything here. Then we went ahead and verified it because of this published source. So if we grab this address, lottery deployed it here, we jump over to ring-b Etherscan, we paste this address in here, we'll see this contract with the little check mark is verified. And again, we'll go to the read contract. We can see all the public variables and all the public functions. We can go to write contract and we'll see all the transacting functions that we can interact with. After we get verified and things get deployed, we went ahead and called our start lottery function to actually start the lottery. We got our little print line saying the lottery started. Then you entered the lottery. We then funded the contract with Link so that we could get our random winner back. And then right now our end lottery is confirmed. And we're just waiting this 60 seconds, right? Because we did this time.sleep. And if we sit on this contract, if we go to transactions and we refresh, we can actually see some of these different method calls over here. We can see we did a contract creation, we started the lottery, we entered the lottery, and then we recently ended the lottery. And you'll see in our script here, it says 0x blah, blah, blah is the new winner, which is perfect, right? That means that the Chainlink node actually responded. We can actually verify that by looking in the contract. We'll go to read contract. We can go to the recent winner and see somebody did indeed recently win. We can also go to events and we can see some of the events that we created. We can see this first event right here is this requested randomness event. This is the event that we called. And we have this end lottery here. We can also see an ownership transferred function that got called. This was called when we actually deployed this in the first place. Now, a little bit more on these events, aka these logs, right? So topic 0, this hash represents this entire event right here. And this bit is going to be our topic 1, our first topic, which represents that request ID. So this is going to be the request ID. Awesome. We have successfully created a working smart contract lottery with true provable randomness. This is absolutely insane, incredible job here. Now, one additional piece that I want to talk about before we jump off here is, again, in our testing. A file that you're often going to see is what's called conftest.py. Python automatically knows to look for this conftest file, and we'll grab different functions from it. We can also add external plugins, fixtures, hooks, testing root path. It adds a lot of really fantastic features and is a common thing that you'll see. We skipped over it in here for simplicity, but in future projects, you'll probably see this conf test file, which has a lot of really nice testing configuration pieces in it.
Are you as excited as I am right now? Because you just finished lesson 7. You have so many tools at your disposal to be successful as a smart contract engineer. I'm getting more and more excited with each lesson that you complete. So, now that you've done this one, next we actually are going to do 2 back-to-back. One is the Chainlink Mix lesson, and then one is on ERC20s, EIPs, and token standards. So the Chainlink Mix lesson is incredibly short. It's like a couple minutes long. It's really just to show you the Chainlink Brownie mix, to show you what a boilerplate Brownie project looks like. And this is one that I keep up with. This is one that the Chainlink team keeps up with and is always up to date with kind of some of the best tips and tricks for a Brownie project. So after that though, we're gonna go into an ERC20 project, which is also pretty short. And we'll show you how to deploy your own token to the Ethereum, to the Binance, to the Avalanche, to whatever testnet that you want or whatever mainnet that you want. So really looking forward to seeing you in the next one.